Okay, so this is the final section of the course. This is section 5.2, and this is about multiplicity and diagonalization. And this sounds like a totally different topic than 5.1, but it's really not, because multiplicity is something, a word that we're going to use to describe information about eigenvalues, and diagonalization is something we're going to do with eigenvalues and eigenvectors. So really this is a continuation of section 5.1. So we're going to start with the definition, which says the following. And maybe let's do the usual thing where we'll start with an n by n matrix A in the background. So let's say A is an n by n matrix. So this is only going to apply to square matrices. Anything in chapter 5 only applies to square matrices. So we say that A is diagonalizable if the following statement is true. So if, and here's the statement, there exists an invertible matrix P which would also be n by n for this statement to make sense. I'm not going to specifically specify it at this stage, but once I get to the end of the statement, it'll become clear at that point that P would have to be n by n also. So if there's an invertible P and a diagonal matrix D, so remember, a diagonal matrix is just a matrix that all the non-zero entries are on the main diagonal, such that the following is true. Such that P inverse times A times P is equal to D. So in other words, there exists some, well, this isn't really in other words, it's the same words to be honest, but there exists some invertible matrix P and some diagonal matrix D such that this is possible. And it's fairly natural at this stage when you see this definition to think, why on earth would you care if that is possible? And even if it is possible, why would this be useful? And so the real reason that we care about this, at least for our purposes, is the following reason. So if A is diagonalizable, then what can you say? What good is that? Well, here's at least one application. Powers of A are reasonably less demanding to compute than they would be otherwise. So I'll say less computationally demanding in order to evaluate. And why is that the case? And first of all, you should stop for a moment. I'll challenge you to give yourself a job here. It will only take you a couple minutes, but pause this video and do the following. Just write down a 3x3 matrix and then write an exponent on that matrix, maybe say a reasonably high exponent like 7. So write down a 3x3 matrix, put an exponent of 7 on it, and then ask yourself, what would be involved in evaluating that? Remember what a power of a matrix means. It means repeated multiplication. And multiplication of a matrix is no joke. There's a lot of arithmetic involved in computing even the square of a 3x3 matrix. There's a lot of products and sums that you have to evaluate in order to do that. And there's a lot of room for making errors. So if you increase that exponent from a squared to say something like a 7 or an 8, it suddenly becomes apparent that powers of square matrices, even small ones like 3x3, let alone a huge matrix like something like a 7x7 matrix or a 10x10 or a 94x94 matrix, powers of matrices are incredibly demanding to compute, at least by default. But if they're diagonalizable, there's an alternative approach than just trying to brute force it entry by entry. And let me just outline that now. So this is the reason why diagonalizable matrices are a little bit easier to deal with when you're computing their powers. So the first thing I want to remind you of is if you, and I'm not talking about diagonalizable matrices for this number one step here that I read. I'm talking specifically about diagonal matrices. So really strict here. If we're talking about a diagonal matrix, then powers are fairly easy to compute for a diagonal matrix. So let's just remind ourselves of that. So powers of diagonal matrices. I'll just to use fewer words, I'll use the word simple, even though I don't like to use the word simple here because that's a really unclear word. What's simple to one person is not simple to another person. Depends on your frame of mind going into the situation, but I'm just choosing that word because I can finish the sentence on this line if I use that word. But this is the rule that you would use to take a diagonal matrix. Remember the notation for a diagonal matrix? You can use this if I just write diag and then I specify some values. Let's say I've got a value lambda 1, lambda 2, all the way up to lambda n. These are the entries on the main diagonal of my n by n matrix. So that's what this notation means. It means it's an n by n matrix with these are the entries on the main diagonal, and every other entry is taken to be 0. If I raise that matrix to the power of k, which is what that notation means, well, the result is just another diagonal matrix, and I can get it by just raising every single entry on the main diagonal to the power of k. So I'd have lambda 1 to the k, lambda 2 to the k, all the way up to lambda n to the k. So really I just have to take whatever my power is, I can just take each of those entries on the main diagonal to the power of k. Now that's certainly not the case in general, but it works out very nicely for diagonal matrices. So that's the first part of the reason to justify this remark. And the second part of the reason, and the way you connect this fact to the statement that diagonalizable matrices are easier to take their powers. Well, suppose you had a matrix that's diagonalizable. So in other words, let's suppose you could do this. Let's suppose that you could write P inverse A, P equals D for some diagonal matrix D. Well, then what? Well, first of all, I could solve this for A. I could write this as AP is equal to PD just by left multiplying both sides of the equation by the matrix P. And then I could right multiply both sides of the equation by P inverse. And that would give me A is equal to PD P inverse. Well, okay, and that's important because now let's look at what would happen. Let's say I took A squared. Well, then that would be PD P inverse squared, which I can now write as just P D P inverse times P D P inverse. And really I could drop the brackets now and just write this as a string of matrices being multiplied. I'd have P D P inverse, P D P inverse. And then you'd actually see that these P's on the inside, well, P inverse times P is just the identity. So what do you get? You end up with P D D P inverse, which you could write a little bit more compactly as P D squared P inverse. Okay, and it's not maybe quite so obvious why that's a big deal, but let's try A cubed. What would A cubed look like? Well, we'd do the same strategy. You'd have P D P inverse cubed. So write out what that means. If you cube a matrix, that means to multiply it by itself 3 times. So P D P inverse, P D P inverse. Right, that's what you would get. And if I drop the brackets this time, I'd get P D P inverse, P D P inverse, P D P inverse. And then again, observe what's going to cancel. That product is going to be the identity, and this product here is going to be the identity. So if you remove the things that are redundant, you're going to end up with P, D, D, dP inverse. So what does that mean? You get P, D cubed P inverse. And you could start to actually see the pattern here. In general, this is what's going to happen, and you can check this for higher values of the exponents. If you're not immediately convinced that this generalizes, maybe try it for a to the 4 or a to the 5. Copy this strategy and you'll see why this works. But in general, for a positive counting number k, we have the following. A to the k is just p d to the k times p inverse. So in other words, to raise a to an exponent k, it amounts to the following. Take this diagonal matrix D, which exists by part of our assumption. If A is diagonalizable, you can get that diagonal matrix D. Just raise D to the power of k first. And that's not so bad. Raising a diagonal matrix to the power of k is not so bad. Well, then you have to multiply it on the left by p, and then multiply it on the right by p inverse. And yes, that takes some work no matter what. But that's a hell of a lot better than raising a to the power of k, especially if k is large. This is very difficult to compute. D to the k is reasonable to compute, or sorry, d to the k is easy to compute, and then the two matrix multiplications are fairly reasonable. So this cuts down on your work by a lot if either k is large or if the dimensions of A are large. And that's the main reason why we care about diagonal matrices. But there's lots of other applications as well, but that's our main application.